Okay, so today we're going to talk about designing a flipping battle bot. This problem was brought to me by a student a year ago? Yeah, I think a year ago. And the student wanted to design a pancake flipping bot essentially because when you flip the other battle bot on their back and they're disabled, the contest is over. And the way this would work is you have a piston, pneumatic piston, which pushes up on this, pushes up on this lever, which causes the end of the lever to flip up and flip the robot over. Now, if it's successful, the piston has to move with a speed of at least 3.13 meters per second, which means that fluid is traveling through this piping system. It'll end up, we'll see, at a fairly fast rate, which means that there's going to be fairly high viscous losses. And those viscous losses will manifest as a pressure drop across the system that will mean that this piston will not be able to push up as fast, as hard as we want. So we're going to try to figure out what the forces that we can push up with this system, which is the system that the student had designed, when we know that the piston is moving up with a speed of 3.13 meters per second, and then we can decide if that force is enough to actually push a battle bot. I think the maximum weight of these things is 50 pounds, enough to actually push up on this, push it up with an eventual speed of 3.13 meters per second, because it has to accelerate that mass, right, with that force. So if we're going to do this, let's talk about our system here. We have a pump that's running continuously while the battle bot's running around trying to avoid being stabbed by the other bot. And that air is going to come in and fill up this tank because this valve here is closed most of the time. Then this solenoid valve, which is going to open very quickly because this whole thing has to happen very fast. When it opens, air will leave the tank coming down through this tube and coming out here into this piston, which will then start moving up. So we're going to draw our control volume as starting in our tank, going through this tube down this way, through our valve, into our piston, up very close to the piston, and then back through and up here. So that, as we'll see, the air entering our control volume has a negligible velocity because it's a very large area. But the air leaving our control volume in the piston area leaves with a speed that is equal to the piston. So we're going to assume steady state. It is not a steady state system, but we can assume a quasi steady state where we're going to analyze one instant in time. We're going to assume that the density remains relatively constant. It doesn't, but we're going to assume it. Steady state and uniform properties. It becomes a much more difficult problem to solve when we allow the density to vary with time. So equations are going to be equation 1. We are going to have I have to figure out where my notes are because I can't memorize all of these numbers. So our equation 1 is going to be our typical conservation of energy equation. P over rho g plus v squared over 2g plus z out is equal to P over rho g plus v squared over 2g plus z in plus h pump plus negative sum of all of our head losses. And so the particular system we've chosen, V in is 0. The difference in height is negligible. We can neglect it because it's a gas, right? So frankly, the change in height doesn't matter because gas has such a low density. V out is not negligible. P out is important, and P in is set by the maximum pressure allowed. Obviously, the competition does not allow you to have large pressure vessels being stabbed by or cut by other saws that could turn into bombs, right? So they set a maximum pressure that can happen. Cool. The other equation that we're going to use is that force is equal to pressure times area, where this is the area of our piston. And this pressure is our P out. So 1 plus 2 into 3 gives us that, 1 into 3 gives us that P out is equal to, and we're going to solve for this pressure right here, is equal to rho g, oh, nope, I just multiplied that through in my notes, so I'm just going to multiply it through here too, is equal to negative rho b squared out over 2 plus pn minus rho g times the sum of all of our head losses. Cool. So now the important part about this problem is that we have two major head losses. We have a head loss in this first pipe, which is 4 millimeters, and a head loss in the second pipe, which is 8 millimeters. So let's tackle this and figure out what our major head loss friction factors are. Because remember, our goal is always solve for these friction factors. So we have to solve, in order to go through this whole thing, we have to solve for what our V is. We're going to do our major head loss 2, which is the head loss in our thicker pipe here. We're going to do it first. So velocity is equal to V piston times A piston divided by A tube, which is going to be equal to 3.13, right? 3.13 meters per second times pi times 0.02 meters squared divided by 4. And all that is going to be over pi times 0.008 meters squared divided by 4. Now, luckily, the 4's cancel out, the pi's cancel out. We can just plug this in, and we get a speed of 19.5 meters per second. We can plug that into our Reynolds number now. We know this is air. We're going to assume a density, rho VD over mu, remember. We're going to assume a density, normal density of air, which is 1.23 kilograms per meter cubed. That is not correct. We are compressing our air a decent amount, but let's assume that for now. And we're going to have 19.5 meters per second as our speed. And our diameter is 0.008 meters. All that's divided by the viscosity, which is 1 times 10 to the negative 5th kilograms per meter second. So our Reynolds number ends up equaling 1.9 times 10 to the 4th. So it's fairly low here. Our E over D value is 0.00025 millimeters divided by 8 millimeters. So this is actually going to be fairly small too. It's equal to 3.12 times 10 to the negative 5th. And when we plug all this into our equation, we get an F of 0.027. Great. Now, looking at our major head loss now, major head loss 2, we have the same stuff, right? Nothing really changes. All we're changing is the diameter. So we can recalculate all this, plugging in a new diameter in all these equations. Instead of 0.008, we're going to plug in 0.004. So our velocity increases actually a significant amount. Our new velocity ends up being 78 meters per second. Now, 19.5, that's actually fairly fast, right? 19.5 meters per second is something on the order of 50 or 45 miles per hour. 78 meters per second is on the order of 150 miles per hour, right? It's quite fast, quite fast. We're almost to the point where compressible effects matter. Our Reynolds number is 3.8 times 10 to the 4th. It is increased with our increased velocity. Even though our diameter has decreased, the increase in velocity was enough to increase the velocity increased more, so our Reynolds number actually increased. E over D is going to increase because our diameter has decreased. So our E over D is 6.24 times 10 to the negative 5th. And the resulting friction factor ends up being 0.017. And that has happened because our E over D has decreased and our Reynolds number has increased. And if you remember, these lines tend to go in this direction like this. So if we're going down and over, we're necessarily going to decrease our friction factor. All right, so we have our friction factors. Now let's plug this stuff in. So, or well, let's look at where we have where we're at on our equations. So if we combine equations 2 and 3 into equation 4, then we get that our force on our piston is equal to our pressure at our inlet minus rho V out squared over 2 minus rho G sum of all of our head losses times A piston. So now the fun part about this is that now we have to calculate all of our head losses. So to do that, we're going to do that separately here. So this is going to be equation 5. And we're going to calculate all of our head losses. Some of our head losses is equal to F1 L1 over D1 V1 squared over 2G plus F2 L2 over D2 times V2 squared over 2G. Now remember, these two velocities are different because the diameter of our pipe has changed, so our velocity has changed. Now we have to add in our minor loss value, so plus K90 times V. And here it matters, right, what diameter you're at as well. So this is going to be V1 squared over 2G plus our K valve times V1 squared over 2G. And when you look at the valve, you'll notice that the diameter changes across our valve here. So this is a valve that starts with the input's a 4 millimeter input and the output is an 8 millimeter input. And the valve manufacturer will tell you which velocity to use when you're calculating losses due to this valve. So this particular manufacturer said to use the input velocity. So we're going to use V1. And then we have our entrance velocity, which is plus K entrance times V1 squared over 2G. So it turns out all these K values used V1, but that wasn't necessarily true. We could have just as easily had some minor losses that used V2, but they didn't. Great. So if we plug in all of this stuff, we get the sum of our head losses is equal to 1,212 meters. Okay. So now if we plug all of our numbers into our force equation, 5 plus 4 into 6, we get that our force is equal to, it turns out 7 bar is the maximum pressure that you can use. So it's going to be 7 times 101.3 times 10 to the third pascals minus, and here I'm going to try to incorporate some change in pressure. So remember that our we can pressure scales with the density. So P is equal to rho RT, which tells us if our temperature is constant that P over rho 1 is equal to P over rho 2. So if we know our density at atmospheric, so P2 over rho 2. So if we know our density at atmospheric pressure, we know that if we're having 7 times higher pressure, we have to have 7 times higher density. It's just that easy. So if our density at 1 is going to be equal to 7 times 1.23 times 10 to the, that's it, kilograms per meter cubed, times our velocity squared, so 3.13 meters per second squared divided by 2, minus 9.8 meters per second squared times 7 times 1.23 times 1.23 kilograms per meter cubed. I don't know why I keep trying to get that to scientific notation. Times all of our head losses, which is 1.12, or sorry, not 1.12, 1,212 meters. And all of this has to be multiplied by the area of our piston, which is pi times 0.02 meters squared divided by 4. All right, so I'm just going to double check. Yep, you guys can all see that. So if we plug in our answer here, we find out that the force applied by our piston at the maximum velocity of that piston, so this will be higher when the piston just starts moving, is equal to 191 newtons. And again, I have no idea if that's high enough force. At first guess, I'm guessing it's not enough. If we want to do a quick back of the envelope calculation here, we're going to estimate our force is equal to mass times acceleration. If our maximum mass is 50 pounds, and this is going to be about 20 kilograms. So we're going to say our force is equal to 20 kilograms. And then we have to figure out our acceleration. And this acceleration has to be quite high. It has to be at least 2 or 3 times the acceleration due to gravity. So we're going to assume this is, let's just pick 20 meters per second squared as an introductory guess. The force that the spatula has to apply is equal to 400 newtons. Now, the way we've set up this lever arm, where we have our pivot here, here's our spatula, and we're applying our force here, our force is going to be lowered, right? We're going to be magnifying the distance moved, but decreasing the force applied. So our F has to be greater than 400 newtons. And my guess is a decent amount greater. So if your piston is halfway between here, our force would have to be twice as much as 400 newtons, which means our F would have to be equal to 800 newtons. So first of all, these people, these people, when they're designing this system, have to use a piston that is much larger in order to achieve their goals. But here's the really interesting part. So here's the F at the maximum speed. The F, if we neglect losses, so this is going to be also equal to F at the start, before it starts moving, before there's really much head losses because our fluid is not moving fast, right? F start is going to be equal to 223 newtons. So these people are losing 15% of their force due to head losses. If they increase their piston size, right? If they increase their piston size, they can increase the amount of force, right? Because force is equal to pressure times area, and their pressure is fixed. If they increase their piston size, unfortunately, what that does is that increases the velocity of the fluid everywhere, because we're fixed at the velocity of our piston. Our piston cannot go slower than 3.13 meters per second in order for this to work. So as they increase their piston size, they increase their area here. And that area, if they double their area, increases their force. But that area also increases their velocity, because as you remember, we increased our area was equal to our velocity in each of our pipes was equal to our velocity of our piston times our area of our piston divided by the area of the tube. So what can these people, so the end result is in order to increase your force by a factor of 4, you have to increase your area by a factor of 4. But if you're increasing your area by a factor of 4, you're also increasing your velocities by a factor of 4. And suddenly now your 78 meters per second becomes a roughly 300 meters per second, which is about the speed of sound, which is not feasible, right? You're going to start getting major compressible flow effects, which means you might even start getting shocks in your system, which will severely limit your flow rate. Yeah, which is just terrible. So the only option for the people who are designing the system is to increase the diameter of all of your tubes, right? All of your tubes, all of your corners, your valve has to be bigger. Everything has to be bigger in order to decrease your losses. And what that does is that increases the area of your tubes, which will decrease your velocity. The decreased velocity decreases your Reynolds number, and it also decreases your E over D, which allows your friction factor to go down. The friction factor going down is not a big deal, right? The bigger deal is that this friction factor is multiplied by a V squared over 2G and divided by your diameter. So if your diameter goes up, this goes the entire thing goes down. Your velocity is going down. This entire thing goes down by v squared. So you're getting triple effect from just increasing your diameter. And that applies for everything here. Your v1 squared goes down. Your loss due to the 90-degree corner. Your loss due to the valve. Your loss due to the entrance. Everything goes down significantly, and so you can drive your head losses much lower, and you don't have to worry about losing 15% of your force. You can probably even go down more than that. Now, the downside of this as a designer is that larger components cost more money, right? So larger components cost more money. That's not such a big deal with a battle bot. The increase in cost is not going to be significant enough to dissuade them from doing this. The other downside is that as you turn on this valve here, you have more dead volume inside of your tube that has to be filled up. So what you would do is you would push this valve to be as close to your piston as possible so that when you open it, you don't have air rushing into this long tube. The air immediately goes into your valve, your piston, and does work, useful work, as opposed to the work of filling up the tube with dense air, high pressure dense air first. So you would minimize this length here as much as possible, move this valve as close as possible to the piston, and then open up everything in order to get as low of losses as possible. But I love this example. It makes me so happy because the main thing I want you guys to take away is that viscous losses do matter, right? They matter a significant amount. You lost 15% of your forces in this, and we weren't even close to being able to solve this problem. When you actually, using the components they picked out, if they were to just make the piston larger, this system would not work. You'd lose probably 50% of your force, if not more, through viscous losses, which means it's just impossible to do. You simply could not produce the force you needed to using the components picked out. And the other reason I love it is that using a tool you've learned in this class, you can estimate the design requirements for something actually practical, right? So you could sit here and go, all right, this isn't going to work. Scratch this, move over, up the diameters on everything, up the diameter on the piston, and yeah, up the diameter on the piston. And you know that you're going to be closer to your solution because this actually works, right? This actually works. All right, that is the end of that example.